Hello students, in this video we'll prove that complex Taylor series define holomorphic functions in their disk of convergence. Let's be given a series, looks like this, f of z is the sum, n goes from 0 to infinity, of some numbers a n times z minus a center c to the power n. So I've defined f via this Taylor series of complex valued numbers, right? And remember, we have this formula over here. We have 1 over r is equal to the lim sup, as n tends to infinity, of these coefficients, a n to the 1 over n, right? And we know from a previous video that if modulus of z, of course, this can be between 0 and 0 to infinity inclusive. Let's just assume the finite case, the infinite case is even easier, right? So in other words, what we're going to do is we're going to say that if modulus of z is less than or strictly less than r, then modulus of z, if modulus of z minus c is strictly less than r, then the series converges. The series converges absolutely. Okay, excellent. And so now what I'd like to do is I'd like to say that if you're less than r, strictly less than r, then the derivative, the term-by-term derivative series will converge also. So we claim, and just for the sake of simplicity, right, we're going to do the standard thing we do. We're just going to choose c to be 0, right? So we can choose c to be 0 and c to be 0 so that we're centered at the origin. Otherwise, all the arguments work exactly the same just by carrying around the modulus of z to the power c. Nothing else changes, okay? All right, so we claim f is holomorphic. So I claim that this function f is holomorphic where? In this region, in modulus of z less than r. And moreover, f prime of z is equal to the sum, n goes from 1 to infinity, of n times a n times z, well in this case I should have z to the power n minus 1, right? What you would expect to get by term differentiation, okay? And moreover, what do we know? I know that the lim sup of a n to the 1 over n is the same thing as lim sup of a n to the 1 over n times n, right? And so that's just a note, that's a good calculus exercise, right? So remark or note. So now I'll use some other notation, right? So for those of you who've seen some analysis, this also means lim sup, right? Lim sup of a n to the 1 over n is trivially equal to the lim sup, as n goes to infinity, of n times a n to the 1 over n. Because 1 over n to the 1 over n tends to 1, that's a convergent series, right? With this property for convergent series and lim sups, right? Okay, excellent. So that means that r is equal in both cases, right? So the rays of convergence of this series over here, this converges if modulus of z is less than r. So the same radius of convergence is valid, okay? So we're going to use the same argument as before, so we're going to think of the standard configuration. So here's z equals r. Here's our circle of radius r. Then I'm going to draw a smaller circle over here. Of radius rho, where rho is less than r. And one more tiny circle, right? Here's my last tiny circle. That's a circle of radius little r, right? So let me suppose, so in our configuration, r is less than, rho is less than r, which means the reciprocal relationship there hold 1 over r bigger than 1 over rho, bigger than 1 over r, right? So in other words, I'm assuming that configuration. And let's assume that modulus of z and modulus of w are less than little r. So in other words, if we're in the region, if we're in this modulus of z less than r, I can assume that modulus of z and modulus of w less than some little r, which is smaller than that, and there's a little bit of a bigger rho, right? So in other words, you first find z and w in the disk, right? Then you draw a circle of radius r around them. Then there's still a little annulus left over, and you can squeeze a disk of a circle of radius rho in between in that annulus, right? That's a property of open sets in the complex plane, okay? Excellent. And so now what's the idea? The idea is that, let's consider this difference quotient. F of z minus f of w over z minus w. That's our difference quotient, right? If I want to show the derivative exists, I want to show the limit as z tends to w. So here w is fixed in that disk, right? So here's z and w, modulus of z and modulus of w are less than r, right? So we're going to assume this condition over here. And then what will this look like? Well, I can simply just plug it into this series over here. So in other words, the series an z to the power n. So this is going to be a what? This is going to be the sum. N goes from 0 to infinity. Then we'll have an an. Then we'll have a what? We'll have a z to the n, z to the power n, minus w to the power n over z minus w. Okay? So in other words, that's what this difference quotient is, right? Now the key is to write this I know that z minus w can be this. I can actually factor this thing over here, right? And so if we factor this, what do we get? If we factor this, we're going to get the following expression. The sum n goes from 0 to infinity, and then an. And then we'll have a z to the n minus 1 plus z to the n minus 2w plus z to the n minus 3w squared plus zw to the n minus 2 plus w to the n minus 1, right? So in order to just factor that out, okay, because w is a root of this polynomial, right? So I just do synthetic division if I wish, right? Okay, so that's what it looks like over here. And so now let's look at these terms over here, right? So what can I say about those terms? I know those terms basically look like what? Those terms over here look like a power of r. How many? We have n terms over here, so there's n terms, total terms. Each of them, each bounded by what? By r to the power n minus 1 in modulus. Okay, so there's n terms bound by r to the power n over here, right? So in other words, let's look at the terms in this expression over here, right? So in other words, an, modulus an. And what's one other thing we know? We know that modulus an is eventually less than or equal to what? Is eventually less than or equal to 1 over rho, right? An less than 1 over rho to the n for n sufficiently large, right? Okay, that just follows from the lim sup, because I know the lim sup of this an is equal to 1 over r, right? And 1 over r is strictly less than 1 over rho, so eventually they're less than 1 over rho, right? Okay, good, that's the key feature. All right, so now let's estimate the terms in this series over here. So let's look at a modulus an times this expression over here. So what does that look like? So modulus an times all those terms times zn minus 1, yada, 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 all the way down to what? All the way down to what? All the way down to, and if you want this to be true for all those, then you can replace it with a constant too, right? W to the n minus 1, like that, is less than or equal to. And let's just say this is for all n, so we can replace this with a constant m, right? So in other words, I can say there's a constant over rho to the power n. And then how you choose that constant for the first n of those terms, just choose the an's are all numbers, right? So they're all multiples of these things. Choose the supremum of those numbers for the first n of them, and that supremum is actually a maximum, okay? Less than or equal to what? Less than or equal to n for these terms over here. Then I'm going to have a what? Then r to the power n minus 1, and then a 1 over rho to the power n. 1 over rho to the power n, like that. Good. And so now, of course, we can compute the nth root of this thing over here. So now consider the nth root of this expression. One over n is less than or equal to what? The nth root of 1 over n, and then the nth root of what? And then the nth root of r to the n minus 1 over rho to the n, right? And so as n tends to infinity, what's happening is n tends to infinity. This expression over here is n tends to infinity. This converges to, as n tends to infinity, what? It turns into just an r over rho. And r over rho is strictly less than 1, right? So the nth root of this thing as n goes to infinity, so in other words, the lim sup as n goes to infinity of this thing is what? Is less than or equal to 1, right? In other words, this series is going to converge to something that's less than 1. So in other words, by the root test, this is going to converge uniformly. So now I have it bounded, in other words, by the Weierstrass M test, right? So in other words, the Weierstrass M test, so that gives me my bounds. So hence, the Weierstrass M test implies that this convergence is uniform, right? As what? as w and z get close to each other, right? As n goes to infinity and z converges to w, right? So in other words, once I have uniform convergence, I can pass this limit through, right? So in other words, the limit f prime of w, which is the limit as z converges to w, f of z minus f of w over z minus w is what? Is going to be the sum over here. And of course, now when I do this over here, I have to let n go to 1, right? N goes from 1 to infinity of the limit as z goes to w of an, and then z to the n minus 1 plus w to the n minus 1. Good. And that's just going to be what? That's just going to be the sum. N goes from 1 to infinity of an times w to the power n minus 1, which is exactly the formula we have right over here. I just have a z instead of a w over here. So in other words, the key thing is that we have uniform convergence, right? The series converges, and it's actually going to converge uniformly by the Weierstrass m-test, right? So in other words, we have a beautiful result. We have uniform convergence, and when you have uniform convergence, you can put limits inside of infinite series or inside of integrals, right? So that's the key feature of this, and we recall from real analysis that whenever you have uniform convergence is essential, you can interchange limits in sums and limits in integrals. So so the Weierstrass m-test and this idea of like inserting another open disk inside the intermediary open disk to get a uniform estimate is essential to prove the derivative exists. Now this is excellent, because now what do we have? Now I have a full arsenal of holomorphic functions. If I have a convergent power series, right? Convergent power series whose radius of convergence r is either, if r is infinity or if r is finite and non-zero, then I know that inside that disk of radius r, this function is well defined, and moreover its derivative exists and is given by this formula over here, so its derivative is well defined, therefore it's holomorphic. And of course, once I do this, I can turn the crank and get a formula for all the derivatives of the function. So the beautiful thing about this particular, I'll call it a class of holomorphic functions, even though all holomorphic functions have this property. Right now at this juncture we don't know that, but this class of holomorphic functions has the property that not only are they holomorphic and differentiable, but they're second differentiable, they're third differentiable, they're fourth differentiable. So this is an illustration of what's known as elliptic regularity, where if I give you sort of rough initial data, the structure of the solution, the Green's function, or in this case what's known as the Cauchy kernel, which we'll see in further videos, basically is an instantaneous regularization mechanism, and it not only uses regularization, it gives you an analyticity, right? So beautiful, beautiful theory. So this differential operator, which a priori says all I'm asking to be holomorphic is I want a derivative to exist. For this class of holomorphic functions, that shows that not only does their derivative exist, but their second derivative, third derivative, fourth derivative, fifth derivative exists. That's a huge amount of information that you gain from this, and that's going to open the door to proving lots of beautiful estimates and really classifying the structure of holomorphic functions. Thank you very much.